Welcome to your next titration video. Just a heads up, this is going to be the longest one yet, and every video after this should be pretty short. So just make it through this one, you're going to be okay. So this will be a weak acid plus a strong base, or a weak base plus a strong acid titration. Same method either way. Let's figure out which one this is. We have 25 milliliters of 0.1 molarity acetic acid, strong or weak acid. That is weak. Plus sodium hydroxide. Okay, so we've got this one here. Weak acid plus strong base. That's what we're doing. It's being titrated with sodium hydroxide. So that means, just a quick little doodle over here, we've got a little beaker full of our acetic acid. And then we are titrating it with NaOH. That's what's happening. That's an awful drawing. Oh well. So we're going to first figure out the initial pH of just the acetic acid. It's weak, and then we're going to figure out the pH as we add more and more of our strong base. So step 1, as usual, identify the major species. So we're going to work with acetic acid, which we know is not strong. And we'll also work with NaOH, which we know is strong, but it's a base. Titrations, it's always an acid with a base or a base with an acid. Okay, so now we need our reaction. This problem's a little bit more complicated than the last one because we have a weak substance, which means we do have equilibrium involved. I can hear everyone groaning. Yep. So CH3COOH is reacting with sodium hydroxide to form a salt, NaCH3COO plus H2O. Okay, so now we want our net ionic. So looking above, let's see what will split apart and what won't. Do weak acids get split apart in net ionics? No, they don't. And then let's see, sodium hydroxide, we know that's going to split apart because it's strong. And we also know that our sodium acetate will also split because it's a salt. So that means our sodium will cancel out with each other, so I'm leaving those out. However, this hydroxide isn't going to have another hydroxide to cancel out with, so there's that. And then we have the leftover acetate that the sodium left behind. Now, if you need to write out this full process before getting the net, I don't blame you. I'm just trying to save some time right now. Okay, here's a little bit of a spoiler. We are also going to need the equation just for the initial substance. So we're just dealing with the acetic acid. So initial substance. So we know we have CH3COOH. You're going to need this when you are working with an initial substance that is a weak substance. So I'm using my double-sided arrow. I had some people ask me in class if this double-sided arrow is the same thing as this. And yes, they are the exact same thing. It just depends on the mood, what I write down. Okay, so I needed that because I'm working with a weak initial substance. So now we're going to go through the different parts of this problem. Let's see. My goal is to figure out the initial pH, and in order to do that, I need to know how many hydrogens I have initially, which means I'm working with my initial substance equation. Well, that goes to equilibrium, so in order to figure it out, I need an equilibrium expression. So I know that the K Ka is equal to the products of the reactants. Now, the Ka value would be given to you, and I'm just going to give it to you right now. It's 1.76 times 10 to the negative fifth. Remind me, I need to get you guys that chart of all the different Kas and Kbs. Ooh, and there goes my color coding. Oh, well. So, step 4. Now we're going to use an ice chart to figure out those concentrations. So, we have I, C, E, and CH3COOH, double-sided arrow, CH3COO minus plus the hydrogens it releases. Okay, I know I started off, it told me initially it's 0.100 molarity, and it hasn't reacted yet, so I don't have any of these guys. I don't know my values here. Remember, for weak substances, you do have to use these x's because you don't know how much it ends with exactly. So 0.100 minus x, x, x. Okay, so now that we've done that, we need to figure out what x is equal to. By plugging into the equilibrium expression. So I know 1.76 times 10 to the negative 5 is equal to x squared over 0.100 minus x. Times 10 to the negative 5, that's pretty small. So let's go ahead and assume x is small. Again, this is always somewhat of a risk, but I'm going to take that risk, which you know probably means it's going to work out. So, yeah. So you'll end up, if you do that, you'll end up crossing out the x that's being compared to something else. So you'll end up with an x that's equal to 0.0013, I want 3 sig figs? 133. I know x is equal to the concentration of hydrogen, so there it is. I have to prove that this is valid using the 5% rule, so I'm going to say x over what it's being compared to times 100. So that's 0.00133 over 0.100 times 100. That needs to be less than or equal to 5%. So let's see what we get. You end up with 1.33%, which is less than or equal to 5%, so we are good to go. On your tests, not this last one, the equilibrium one, I saw some people trying to plug in K here instead of x. Make sure you're putting x over what it's being compared to. It is not K over what it's being compared to. X over what it's being compared to. Okay, so now that I know my hydrogen concentration for the initial substance, I can solve for the initial pH. So you'll have pH is equal to the negative log of the concentration of your hydrogen ions. You're going to get 2. We want 3 sig figs, so 877. And that is for part A. Woo, okay, there's part A. Now part B. We're going to solve for the pH. After 10 milliliters of NaOH is added. Okay, so in order to do that, we have to first do the dilution, because we know we are mixing together two different volumes. So we'd have initially 0.100 molarity times initial volume of 25 milliliters is equal to M2 times its new volume, 25 plus the new 10 gives us 35. We are assuming that volumes are additive when we do these. We don't want to torture you too badly. 714. Okay, so there's your concentration of acetic acid. Now I cannot I cannot immediately say, oh, well that means I have that much hydrogen, because why? Because it's a weak substance. We cannot just jump to conclusions there. We have to use an ice chart. So let's figure out the sodium hydroxide ones though. 0.100 times its initial concentration, that's how much we've added. 35. Oh, I'm being weird about units. Oh well. That is not a concern right now. 0.0286 molarity sodium hydroxide. So this is strong, which means I know these are the concentrations of its ions right away. I don't have to make an ice chart to figure that out. Okay, so I am now going to have to, let me just look ahead and make sure. Yeah, I'm going to have to create an ice chart to figure out my concentration of hydroxide ions. This is going to be pretty similar to the previous problem from this point forward. So, ice chart. Now remember, we have a common ion here. We have the acetic acid, which is providing hydroxides, but we also have hydroxides coming out of the sodium hydroxide. So when we write this out, we'd have ICE, and we'd have CH3. So right now, what I'm using is my net ionic. I'm no longer dealing with just acetic acid. I now also have sodium hydroxide being added. So here this is double-sided because we are dealing with something that is weak being mixed in there. I'll have CH3COO minus plus H2O. So we only needed that initial reaction just for solving for the initial pH. We're moving on to the net ionic. Put a star here. Net ionic. Now that we have started adding our sodium hydroxide. So my initial concentration of my weak acid I got from my dilution. My hydroxide concentration is coming from my sodium hydroxide, so that's 0.0286. And I don't have any of my acetate ion yet, and I know I don't include water. Okay, so here we know that the hydroxide is our limiting reactant, so this goes away. So that's right, X's are no longer a problem. We could just do this. So if that happens, I know I'm going to add 0.0286. Oh, here, let's try to, oops. This is our change, and now E. I was optimistic about how small I could write. So we have 0.0428. We don't have any hydroxides left, and we know we have 0.0286 of our acetate ion. Okay, so we have one new step. We need to solve for the pH. But if you remember from the buffers notes video, when you are dealing with a weak acid and a strong base, you are creating something that is like a buffer solution, which means we have to use the Henderson Hasselbalch. That probably is Hasselbach, but I'll just sound incredibly ignorant and say Hasselbalch. So we know from this equation that the pH is equal to the negative log of the Ka of your weak substance plus the log of the concentration of your ion over the concentration of your weak acid. So let's plug in some numbers. pH is equal to the negative log of the Ka, which was given earlier as 1.76 times 10 to the negative 5, plus the log of, so this comes from the ice chart, the A minus is the acetate ion, so 0.0286. The initial ion was our acetic acid, 0.0428. And if you plug in this mess, you end up with a pH of 4.579. So this is the pH when you have added a small amount of our strong base to our weak acid. So take note, when you are doing problems that involve a weak substance with a strong substance and it's a titration, you need to use the Henderson-Hasselbalch equation. All right, moving on. Now we're going to do this again. Solve for the pH, but this time it's after 12.5 milliliters of 0.100 molarity NaOH is added. Okay, so I'm just going to read out our steps. We will dilute, we will make an ice chart, we will use the Henderson-Hasselbalch, and then we will solve for, and then we'll move on, actually. Then we'll do another dilution, set up an ice chart, and keep going. So it's pretty repetitive. This step is the same as the last one, so you can do step 8 without me, but make sure you come back for step 9. So, dilution, CH3COOH, 0.100. I'm not going to give you as many details here because it is the same as last time. So you'll come out with an M2 of 0.0667 molarity acetic acid. I'm not going to split it into its ions here because it is a weak substance. However, our strong base, we know exactly what it ionizes to form. So for that one, I will write out the concentration of each of its ions. So I'll get an initial concentration here of sodium and hydroxide. Okay, so now that I've done my dilution, I'll make my ice chart. ICE. And remember, we will use the net ionic here, so CH3COOH is going to react with hydroxide, and it's going to form CH3COO minus, and we're not going to include water. So we have, getting this from my dilution, and I don't have any of that yet. I need to look at what my limiting reactant is, which in this case is whatever is the smallest. That's always how it works. so I will lose that many hydroxides. It's 1 to 1, so that's exactly how much acetic acid will react, and that's exactly how much of the acetate ion will form. So you end up with negative 0.0333, nothing, and 0.0333. So now that we have our concentrations, we can utilize the Henderson-Hasselbalch equation there's not two A's there. So the pH is equal to the negative log of the Ka, so it's still 1.76 times 10 to the negative 5 plus the log of the ion, so that's my acetate, over the, oh, that shouldn't be negative. I'm adding a plus sign over here on my ice chart. We're just getting rid of it. There. Over my original 0.0333, and ooh, these come out to 1, and we know the log of 1 is just 0. So we end up with 4.754, which is when you could also say this is when the pH is equal to the pKa, which we know happens at the 1/2 equivalence volume. 1/2 equivalence volume. If you go back to the titration notes, you will see the graph of the poly product that does this like many times, and there is a part on the graph where I say, oh look, over here the pH is equal to the pKa. So go back and find that in your notes. But anyway, this is our pH. This is our answer to part, I don't even know what part we're on anymore. After 15 milliliters have been added, woo! Oh, 15, 20, 12 and a half, sorry, that's C. This was C. Okay, cool. We are getting there. If you are zoning out and doing this on your own, come back to us. Step 9's a little different. Solve for the pH after 25 milliliters of NaOH is added. So, as usual, dilution first. So, CH3COOH starts off at 0.100. Then we have 25 milliliters. Originally, we're adding another 25 milliliters, so M2 at 50. So M2 is equal to 0.0500 molarity acetic acid, which I don't split into its ions because it's a weak substance. However, this one is strong, so I can, I can write out the ion concentration. So, oh, would you look at that? The concentrations are equal to each other. Interesting. Okay, now we're going to set up an ice chart. I promise this is going to get different in a second, so please don't leave me. ICE CH3COOH We're using the net ionic here because we have combined two different substances, so we want the equation that shows the two different substances reacting. H2O, non-existent, so we have 0.0500, 0.0500, and nothing. And oh, they are equal to each other. So there's no limiting reactant. This one gets added. Okay, so in this situation, last time when we had no hydroxides or hydrogens being produced within our ice chart, we then went to the autoionization of water to figure out our concentration. We used the concentration of hydrogens times the concentration of hydroxides gives us our total concentration. In this case, since we do have some of our acetate ion and we know it's reversible, which means it could go back the other way, it could produce some hydroxides. So let's write this step. It's called autoionization step. So we know that autoionization, this is like a, here, let's get a different color. So this autoionization, you definitely want to write this down for yourself. Autoionization occurs at the VE, which is equivalence volume. For weak plus strong reactions. Autoionization occurs at the equivalence volume, so that's when their volumes are equal. We had 25 milliliters of our weak acid, 25 milliliters, and we had 25 milliliters of our strong base, so the volumes are equal. So autoionization will occur here, which means we're going to have a slightly different ice chart than usual. I'll keep using a different color. So ICE. Hopefully people who are fast forwarding will stop fast forwarding when they see this jarring blue. So what you're going to do is you're going to go back to your equation that only involves the weak substance. And, oh sorry, I misworded that. You're going to flip your net ionic to where the weak substance's ion is first. So here, let's like draw a little arrow and show reversed. We are showing now that our acetate ion can provide us with some hydroxides. So here we'll plug in that we had 0.0500 molarity from that ice chart up there, and we didn't have any of these. However, in this case, it is a completely weak substance. We don't know anything about what's going to be produced, so I have to use X's. X's. Okay, so from here, we're almost done. We're moving on to step D, so let's get that going, where we use these X's in our equilibrium expression. So we know, well, let's write one for this. It's going to be x squared over 0.0500 minus x. And this is the reverse of our original Ka. So you could use Ka times Kb is equal to 1.0 times 10 to the negative 14th, or you could just look it up in a chart. You'd end up with this number. So here we have, this is considered to be a KB because it's the other way around. So if you solve for x here, you would end up with 5.3 times 10 to the negative 6. That's your molarity of hydroxide ions. We did that by using the small x assumption. Be careful how you abbreviate assumption, by the way. You know who you are. So 5.3 times 10 to the negative 6 over what it's being compared to times 100. Let's see what that is. You end up with a very small number of 0.0106%, so we are good. Okay, so we know the concentration of our hydroxides, which allows us to solve for the pH, which is what the question asked for. So let's go through the steps. pOH is equal to the negative log of 5.3 times 10 to the negative 6. So you end up with a pH of 14. We know it's exactly 14. 276. 8.724. Okay, so you don't need the Henderson-Hasselbalch here because we know, I'll just go back a little bit. So this is when you don't use the Henderson-Hasselbalch equation. When you are at the equivalence volume, the volumes are equal to each other, you end up with the 0 hydroxide ions being left over at the end. So instead you have to do the autoionization of your original substance and use that to figure out, well, it's going to go backwards. How many hydroxides will it leave in the reaction? And you can then use that concentration to figure out your pH. That was part D, I think. Oh boy. All right. Last step. Last part. Solve for the pH when 35 milliliters of NaOH is added. So first dilution as usual. So we have CH3COOH gives us so you end up with the concentration equal to 0.04167. Oh, 3 sig figs. 0.0417 CH3COOH, not splitting it up because it's weak. Zero, 35 is being added. You'll end up with an M2. I want 3 sig figs, so 0.0583. And it's a strong, so I can say, oh, that's what the ion concentrations were. Okay, so now let's set up our ice chart. ICE CH3COOH. If I go back and find out that this video was not recording sound, I'm going to cry. You might not see me tomorrow on Monday. I'll just be crying at home. Okay, so in this situation, we have we have more of our base than we do of our weak substance. And because of that, I know that my weak substance is going to get completely used up. That is a little note that you could add for yourself. When the volume of your base is larger than the volume of your weak acid, I know that my weak acid is going to get completely used up. So in that case, I'll just use a one-sided arrow, because once that weak substance gets completely used up, it's not going to go back. So I'll put in my concentrations, and this one is 0.0583. I don't have any of that yet. Water is a loser. And so since I know it gets completely used up, I can use that here, and it's my limiting reactant, 0.04167 plus 0.04167. Gone. 167, and that becomes 0.04167. Okay, so since I no longer have any of my weak substance, I no longer have to use the Henderson-Hasselbalch equation. I'll write a note at the end of this to help you figure out when you need that equation. But for now, just accept it. POH is equal to the negative log of the OH concentration. So you end up with a pH equal to 14 minus 1.778, which gives you 12.222. It's equal to your pH. That is your step E. Okay, let's draw a titration. Well, we're going to draw a titration curve, but let's write a note about when you need to use the Henderson-Hasselbalch equation. Use Henderson Hasselbalch, there's an L there, I think, when ice chart leaves you with excess, which means greater than 0, weak acid or base. So if you have an excess of your weak acid, or if you're working with a weak base, then you must use the Henderson-Hasselbalch when you're figuring out the pH. However, if there is none left over, like there wasn't in the last two steps, then you're not going to need to use it at all. Okay, so now let's just, as an aside, let's draw a titration curve, because you should know how to do that. That'll be our step 11, and then I promise we are done. So let's see. A ruler probably would be a good idea. Here we're going to graph the volume of the titrant versus pH. Okay, we know that it started at a concentration below, like between 2 and 3. So here, and it's going to go like this. Whoosh. And we know that within this region, around the 1/2 VE, which is, we should have noted that on here. Let's find it. There it is. Here. When we ended up with the same concentrations within our Henderson-Hasselbalch equation, around that point, that is the buffer region, centered around that point. That is important. You could also label the equivalence point on here, and we know that when you have a weak acid plus a strong base. The equivalence point volume should yield a pH that is basic or acidic. It should be basic, greater than 7. So let's go back and find that. When they had equal volumes, so 25 and 25, here it is, equivalence right here. They had equal volumes, 25 and 25. So what was the pH there? 8.724, look at that. So it worked out. So we'd want on our graph, whoops, daisy, this right here should be 8 should be down here, and 9 should be up there. And this up here was a 3. Okay, there you go. So, oops, I promise that is not going to be, it's never going to be this long again. See you later.